Hi, welcome to another lecture in pre-calculus. Today we are going to talk about inverse functions. Let's go ahead, take a look at the question Alex has for us for this question topic. So the question is the following: determine whether the two given functions are inverses of each other. So two functions are given, such as 4x and x over 4. Are they inverses of each other? Here's another function, 2x plus 5 and x minus 5 over 2. Are these two inverses of each other? The way we are asked to do this thing is by the following construction: f of g of x and g of f of x. That is supposed to give us a clue, and we are asked to calculate these two and decide based on that if they are inverses of each other or not. The problem is simple enough for you to be able to answer it right away, but let me go ahead and expand this thing as a matter of review of several issues all at the same time. So here are the topics we are going to talk about: composition of functions, and then inverse functions. Under inverse functions, we are going to talk about their definition, the notation we are going to use, how do we find an inverse function, how do we verify that something is inverse of something else, and what is it that we need to know about the graphs of inverse functions. So first off, let's go ahead and describe inverse functions in simple terms, and this one by itself might be enough for answering the question we had on Alex. You have noticed from time that you started taking algebra that many functions come in pairs. So we have certain pairs of functions that appear to be undoing the effect of each other. What do we mean by that? For example, x plus 3 and x minus 3. Well, if you add 3 to something and then later on subtract 3 from the result of the previous one, you go back where you started with. So these two kind of undo each other, and they can be called inverse functions of each other. Same is with 3x and x over 3. Multiplication and division are inverses of each other, same way addition subtractions were. So if you triple something and then divide by 3, well, then you go back to where you started, and for that reason they can be considered as inverse functions. A bit more complicated, so cube of x, what's the inverse of that? Inverse of that is cube root of x. So if you start with a number and cube it and take the result and cube root that one, then you go back to what you had started. Beyond these kind of functions, more complicated ones, it takes a bit of work to figure out what is the sister or what's the inverse of this function, what's the function that goes hand in hand with that one. Some functions do give us quite a bit of challenge for finding their inverse. But just to have a mental image of what an inverse function is, it's nothing more complicated than a table that you're going to flip around. So for example, if you go to a restaurant or something, you get a menu. So a menu is a good example of a function. It has certain items on it, and those items come with certain prices. Sometimes you look at the items and then you look at the price of that. Sometimes you look at the prices and then you look at item that associates to that price. These are two styles of looking at a set of data. if you want to call the first one the function f, then the reverse operation will need a name similar to what the original one was, and typically this is called f inverse in our notation. So a -1 on top of the name of a function simply means that you're reversing your view and you're going from the second column back to the first column. Okay, so much for simple introduction to inverse functions. For something a bit more sophisticated than that, we have to go and take a look at what the composition of functions was. You probably have seen this thing in pre-calculus 1 or college algebra, and this is going to be just a review of that. So let's just go ahead and quickly review what a composition of function was. Composition. So let's just pick an example. Say f of x is one function. Let's keep it simple, 2x plus 3, and say g of x is another function, that is x squared plus 4. And what we want to do is to find, just like in the problem in Alex, what is f of g of x and what is g of f of x. Functions are like activities. They have an input and they have an output, just like what happens in a factory. In a typical factory, there is an assembly line and one worker works on some raw material and produces some half-finished product, and then that item goes to the second worker who works on the result of the first worker, and then he produces something else, and so on down the line they go. Something similar to that is being imitated in mathematics when we say f of g of x. So f, this interior function, is like the first worker. It takes for him the raw material is x, it produces something and gives the result to f, and then f is the second worker, and then he operates on the output of the first one. This one, f starts working on x and then g works as the second entry. Typically on an assembly line, doesn't make good sense to change the order or reverse the way the assembly line moves, but in mathematics we are just dealing with simple numbers, and we can exchange who goes first, who goes second without much of a issue. In real life, typically that's not the case. Like for example, you put on your socks first and then you wear your shoes. Normally you don't wear your shoes and then go ahead wear your socks later on. It just doesn't make good sense. So mathematically though, we are just operating on numbers, and exchanging the order is just pretty normal. Now we have to be careful about the algebra, and here let me recommend what to do so that you don't get confused as to the steps. Suppose you want to calculate f of g of x. Concentrate on the first worker. Here's a g of x. What does g of x produce? G of x produces x squared plus 2. So just replace. Okay, this is where students get confused as to what's happening because of confusion between two notations. Students think that f is multiplying x squared plus 4. That's not what the function notation is. To avoid that mistake, let me recommend that you do the following. That second function, write it with the x wrapped in a parenthesis on both sides. Color that parenthesis like this. Wherever that parenthesis happens, replace it by this bigger parenthesis. That's all. So what we have to do is going to be twice x squared plus 4 and then plus 3. So So 2x squared plus 8 plus 3, so that looks like it's 2x squared plus 11. Let's make sure we understood this thing. Suppose we look at it the other way. G of f of x. What does that mean? The g of, we look at the output of the interior function. F of x is 2x plus 3. We color it differently. This is 2x plus 3. I'm going to write 2x plus 3. Now what is g of 2x plus 3? Again, this is where students make the biggest mistake. Let me write g of x was x squared plus 4. Go ahead and wrap x's in parentheses on both sides. Whatever that was, just replace it with this bigger box. So now we are going to have 2x plus 3. That has to be squared, and a 4 has to be added to that. Now, do you know how to square something? Let's do it once, and then from now on you are going to do it the quicker style. So squaring means multiply by yourself a second time. So 2x times 2x is 4x squared, 2x times 3 is 6x, and 3 times 2x is again 6x, and 3 times 3 is a 9, plus a 4. So this is 4x squared plus 12x plus 9 plus 4. Quick action. 2x squared is 4x squared, 3 squared is 9, twice the product of the first and second. That's what the 12x coming from. And then we had a 4 to add, so we add them, so we get 4x squared plus 12x plus 13. Notice that these two typically don't have much of anything to do with each other. They're not same or anything like that. F of g of x typically is very different from g of f of x. Okay, what is the idea of inverse function? We imitate what we see here. Two functions that if you compose them, you go back to what you had started with. If you add 3 and subtract 3, you go back to x. If you multiply by 3 and then divide by 3, you go back to x. So the idea of inverse functions is that f and g are called inverse functions if you take the output of g and give it to f, then f is going to undo whatever g has done and give you x back. Other way around, if you take the x, give it to f, and then take that and give it to g, again g is going to undo whatever f has done. The two of them undo whatever the other one has done. Now we have to make it a bit more precise. This is for all x's in the domain of g, and this is for all x's in the domain of f, but never mind. So such pair of functions are called inverse functions. So for example, if f of x is x plus 4 and g of x is x minus 4, then you notice that f of g of x, well, g of x, what was that? G of x? G of x is x minus 4. What does f do? F adds a 4 to whatever comes in. So if it was x minus 4, you add a 4 to it, you get back the x. So f of g of x turns out to be x. That requirement is satisfied. Similarly, if you try g of f of x, you get g of x plus 4. What does g do? Whatever you give to g subtracts a 4 from it. You go back to x. So this property is also satisfied. Okay, next issue. What's the notation we are going to use? A pair of consecutive letters, typical uh, notation that is used, F and G, when we want to kind of make it clear and clean. Sometimes we just want to use one name. We don't want to have two names, one F, one G, but we have to distinguish between them. The notation there is to use a -1 on top of the name of the original one to get the name of its inverse. So if F is your original, then F inverse will be the inverse of that. If you want to not to discriminate against G, if that is your main function, then the inverse of that is going to be called G inverse. Just in preparation for stuff we are going to do later on with trigonometry, we have another notation in trigonometry. We have a bunch of trig functions like sine, cosine, and so on. So sine has an abbreviation SIN. The inverse of that, you can write it sine with a -1 on top of it, or there is another notation, arc sine. There is still another notation, a sine. So this is same as that, that's same as that. These are so in trigonometry we are going to have another notation that is traditionally used. You can see it on your calculators, programming languages, and so on. These are there. Next topic up, again we are just reviewing stuff from Calculus 1. Let's say find the inverse of, what we mean by that is the inverse function of y is equal to 2x plus 3. Just to be clear, we are not talking about the we are not talking about the arithmetic inverse. We are not talking about the reciprocal or anything like that. That's not what we are after. We are finding a function that is the inverse of a given function. Okay, this is simple enough for us to experiment with it by just looking at a table. So let's make a table for this function, just a regular table, 0, 1, 2, 3. For the values of y, we get what, 3 and then 5 and 7 and 9 and so on. So this is a table of values of this function. So as you notice, I started with x and then went to y. What if I want to go backward? Well, if I give you 11 here, you can guess easily it has to go back to 4. Let me go further out. Suppose I give you 101 and ask you what x was associated with that. You can guess, or you can use the formula that you are given. This came because there was an x that you took and plugged into this formula. So there was a 2x plus 3 that came out to be 101. But you solve it, you subtract the 3, 101 minus 3, and then you divide by 2. I didn't do it so that you see the format, and then of course when you do it, you do get, say, 49. So you get this becomes 49. Well, you can say I can do this for any number. So if you give me y, any number y, any of these things, I do the same thing, subtract 3 divided by 2. So if you have x here, you go to 2x plus 3. That is your function. If you have y, you go backward and then you get y minus 3 over 2. If you want to call f, call this one f inverse, or you want to call this one g, call that g inverse, or whatever. One more thing, which is mostly cosmetic in rather silly in the fact that we always start with letter X. Somehow X occupies a holy position for no good reason really. So if I start with X here, what do I go to? Well, instead of Y, just write X. So it's just cosmetic. There's no mathematical meaning to this. If it was X, then the output will be X minus 3 over 2. In short, if f of x is written as 2x plus 3, then f inverse of x by this reasoning will be x minus 3 over 2. Pause for a second and take a look at this thing. We double first and then add 3. On the way back, we subtract 3 first and divide by 2 at the end. So again, here multiplication happens first, addition next. Here subtraction first, division at the second stage. These are inverses of each other. Well, what if a pair was given to us already and we were just verifying if they are inverses of each other or not? You have an option of repeating what we did here to verify, or you have the option of you have two options. One is to do this, and the other option is to do what we did here. Either of them can be used to verify if a pair that is given to you are inverses of each other or not. So suppose given f of x, say 5x plus 7, and g of x, say x minus 7 over 5, are f and g inverses of each other? That is more or less the question that was on Alex. Let's see, here's my Alex page. So for example, here 2x plus 5 and x minus 5 over 2, are they inverses of each other? Obviously so, by what we just talked about. But how do you go through the steps? Well, one style is to compose the two functions. What is f of g of x? So what we mean, instead of this f x, use output of g, use x minus 7 over 5. So whatever we had here, output of g is given to f. Well, what does f do? Whatever you give it, it multiplies it by 5, and then add 7 to it. Well, 5's cancel, 7's cancel, we get x back. Well, we verified one end. How about the other one? G of f of x, that has to be x as well. G of, what is f? F is 5x plus 7. What does g do? G subtract the 7 that from whatever comes in, subtract 7 and then divide by 5. Again, 7's cancel, 5's cancel, we get the x back. We verified that these two are inverses of each other. One more item before we go, even though that's not in the question there, but we are compressing the topics all at the same time. We are going to make use of this when we come to trigonometry, which is graph of inverse functions. Let me perhaps show this thing on this little software that we have here. So this is Desmos. Let's first draw y equal to x. that is the so-called identity function. What's the inverse of identity? It's just identity again. This function is the inverse of itself. It plays a very crucial role. You notice that this is the function that shows up, excuse me, here. When you compose a function with its inverse, you get the identity. That's what's really happening. So what does identity look like? Well, that's the simplest function. It's just a 45-degree line. Now let's go ahead. I erase this. 2x plus 3. What does it look like? Well, a straight line. What is the inverse of that? We just practiced how to find the inverse. X minus 3 over 2. You look at this, you see something interesting. These two are not two random pictures. If you have one of them, you can get the other one from the first one. Do you see the connection between these two? Let me try another pair for you. So this is half of a parabola, and this is the square root. If you look at that, they are also in a peculiar configuration with respect to each other. Do you see that? Here, let me try a third time. Here's cubing function, here's a cube root function. These two also obey the same property. Here's a give you a hint. See, and the function and its inverse are reflections of each other in the 45-degree line. Let's see it in the other pairs as well. Here is a function and its inverse. They are reflections of each other in the 45-degree line. Here's our third example. These two lines are reflections of each other in that 45-degree line. Let me just go ahead briefly explain that as the last item for today. So graphs of inverse functions are reflections of each other in the 45-degree, meaning y equal to x line. To show that, let me just briefly remind you, let me briefly remind you, if you have a square and you draw a diagonal of that square, then if you think that the diagonal was a mirror, then reflection of half of this square will be the other half. In particular, reflection of this green dot will be that blue dot, and reflection of blue dot in this. So this diagonal, we take it to be the mirror. If this is your mirror, then the two other squares at the two corners are reflections of each other. Now suppose I want to show, here I have a function 2x plus 3 and its inverse, x minus 3 over 2. These are two inverse functions. I want to show that their graph will be reflections of each other. The way to see that is by making tables for them. So I make a table for, say, x and say 2x plus 3, and table for x minus 3 over 2. Let's just be quick with that. 0, 1, 2, 3. I don't need all of these. Let's go get 3, 5, say 7, and what's that, 9. How about there? Easiest way we said to think about inverse function is to take your original table and flip it so it becomes 3, 5, 7, 9. Out it's going to come 0, 1, 2, 3. If you want to use other x's, be my guest, but this is where I'm going to take a look at. Now I say, look at this, 1, 5, and 5, 1. 1 5 is a point on the graph of y is equal to 2x plus 3. 5 1 is a point on the graph of y is equal to x minus 3 over 2. Let's draw both of them at the same time. So I will draw so this is my x and y. 1 5 1 1 2 3 4 5. So I have 1 point here. The other one 5 1 1 2 3 4 5 5 1. Okay, so this was 1 5, this was 5 1. You can make a square. Of course it's going to be 5 5, it's going to be 1 1. In this square you can draw the diagonal, which is just a mirror. By what we said here, 5 1 and 1 5 are reflections of each other in that mirror, and so these two are reflections of each other. 0 3, so 0 1 2 3, and 3 and 0, these are reflections of each other. 2 and 7, 2 and 7 is going to be up here, 7 and 2 is going to be here, and so on. So if you draw the first function here, it looks like something like this, and the second function looks like something like this. The blue and green are reflections of each other in the yellow line, which is what we said. This idea is going to be very helpful when we are going to deal with exponential and logarithms, and when we are dealing with sine and inverse sine and similar functions later on. Graphs of a function and its inverse are reflections of each other in 45-degree line. Reflection is a simple geometrical thing. So if you have spent a lot of time graphing one of these things, you just flip it over 45-degree line and you have the image of the other one. Okay, so we kind of went over a review to talk about all the issues that are involved. The problem that is in front of us, of course, is a lot easier than all the stuff we mentioned, but we need all that background to understand what this thing is, and also we need all of that when we get to more advanced stuff coming up. Okay, so hopefully you go ahead and answer your questions on Alex, and we are going to see each other again in a short bit. Okay, good luck and God bless until the next meeting.